Welcome to the video key for quiz 5. So we've got some water, it's 100 degrees C, and we want to make it be water vapor at 160 degrees C. So whenever you have a problem like that, it is a good idea to do a diagram of heat and temperature. So let's do that now. Okay, so we'll draw a diagram where we've got temperature on one axis and the amount of heat we have to put on the other. And we can imagine, in principle, if we started at a low enough temperature, we'd have to heat up some ice and then melt it, and then heat up the water, and then boil it, and then heat up the vapor. Now we have to see where we are on this curve. Well, we have water at 100 degrees C. So if we label this as solid, liquid, and gas, we're already at the temperature where gas and liquid are at equilibrium, but we only have water, so we're here. It's our starting point. Now we're going to make water vapor, and when we boil the water, it's going to boil and be water at 100 degrees C, and then we're going to have to heat that water vapor up to some new temperature, so we're going to end up here. So that tells us that we have two different processes, which means we're going to have two different terms here. So the Q total is equal to Q boil the water plus Q heat the vapor. So we've got to have both of those terms in there. All right, so we could say that that means that Q, so to boil the water, we're going to take the moles of water and multiply that by the heat of vaporization. So that's something we can look up on our equation sheet. And we've got, to heat up the water vapor, we've got the mass of the vapor, the specific heat of the vapor, and then how much we're going to heat that vapor up. Now, we're not quite done yet because we need to figure out what the N of the water is, how many moles of water we have. But if we take the mass of water and divide it by the molar mass of the water, that will give us the number of moles of water. So now we're ready to plug that in over here, and we can plug numbers in. So the mass of water is 36 grams, and water is 18 grams per mole for water. So we can see our grams are going to cancel, and we're going to end up with moles. So we'll take that, multiply it by our heat of vaporization. So that's 40,600 joules per mole, or 40.6 kilojoules per mole. So we can see that we've got per mole on the bottom, we've got per mole on the top. Those are going to cancel, so we're going to end up with just joules. And then we add heating up the vapor. So we've got 36 grams of water makes 36 grams of vapor. And we look up the specific heat for water vapor on our equation sheet. It looks like it is 2.0 joules per gram per degree C. And our temperature increase is going to be our final temperature of 160 minus 100 degrees. So we can see that we can put in our delta T as 60 degrees C. That's how much the water vapor went up. So now let's plug in those numbers and see what we get for the two different pieces. All right. Oh, it looks like I was wrong about the heat of vaporization. It's 40,700 joules per mole. So anyway, we plug all that in, and so for the first term we get 81 kilojoules. Next one we get 4,000 kilojoules. So if we add this together, look at our data. It's only 2 sig figs. So we can see that this is going to come out to 85. And then we're going to add the other part. We'll get 720 joules, and we've got to round this to 2 sig figs. So we'll say it's 86 kilojoules. And that's our final answer. Okay, so in the next problem, we're going to melt some iron, and we want to calculate the change in entropy of the iron during the process. And we're given some data, and some of it might be useful, some might not be. Okay, so to do this, we know that if we take we want to find the entropy of the iron, the entropy change of the iron, we're not doing any reactions or anything. All we're doing is doing a phase change. And for phase changes, we know the entropy change is the enthalpy change for the iron all over the temperature at which the phase change occurs. So we're melting it, so we'll use the melting temperature. So this equation works for phase transitions. We can't do this for reactions, but we can do it for melting or for boiling. So we need both those things. So first of all, the melting temperature, we know the units for entropy are joules per Kelvin, not joules per degree C. So we got to convert that to Kelvin. So we can see that the melting temperature was 1538 degrees C. And so we're going to add 273.15. And we really don't need all that precision because we don't have that much precision anyway. But anyway, we're going to add that many kelvins, and that is going to end up with our temperature in kelvins. So we've got 273 and 1528. And so we get 1801 is our melting temperature in kelvins. Okay, so we need that, and now we're ready to go. So we've got our delta S is our delta H for the specific transition. In that case, it's going to be we're melting, so it's the heat of fusion. So we've got 13,800 joules per mole. We're dividing by 1801 kelvins. And so when we divide that, we get 7.66. Yeah, 7.66 joules per mole per Kelvin. All right. Number 3, use the data plotted below, all of the data plotted above, to answer the following questions. Note that the equation of a line fit the data is given. All right, so in this equation, we've got a reaction, clearly, because there's an equilibrium constant, and the equilibrium constant is plotted as a function of temperature. So we can go back to the potassium nitrate lab. Remember, we plotted the log of K equilibrium as a function of 1 over T, and we saw that the slope was negative delta H of reaction over R, and the y-intercept was delta S of reaction over R. So we can say y is equal to mx plus b, so we can identify the y-intercept and the slope. And that allows us to do this problem. We really can't do the 2-point form because then you'd just be using two numbers. You weren't supposed to use a line fit to take into account all the data. All right, so we have, going back to the work we just did, we can see that the slope m is equal to negative delta H over R. So if we want to solve for delta H, we have to divide by a negative 1, and we have to multiply by R. So we see that delta H is equal to R times M, and of course we have that negative sign, so we'll put a negative right here. All right, so we can plug that in. We have our negative R, and we're going to use 8.314 because we want joules. Oops. So 8.314 joules per mole per Kelvin. That's our negative R. And then we've got the M, and the M is, let's see, it's right here, negative 3.382. Now we have to decide what the units are on this, and the slope, remember, is equal to the rise over the run. And so we look at the units for the rise and the run to see what the slope's going to be. So the rise, that's the x value, or the y value is the rise. That's a logarithm. We know it's not going to have any units, so let's put a 1 there. If we look at our x, that's the run, that has units of 1 over Kelvin. So I've got 1 over Kelvin, and that's going to be equal to Kelvin. So Kelvin is going to be my unit here. So I've got Kelvin for my slope, and notice that Kelvin's going to cancel my Kelvin, and that's going to give me joules per mole, and that's the unit I want for delta H. So I take my 3.382, and I multiply that by R times negative 1. And so notice that I have a negative slope, but that is going to give me a, because there's two negatives here, it's going to be a positive number. So that's going to give me, that is going to give me 28,000 joules, or 28 kilojoules per mole. Okay, now delta S. To figure out delta S, we look at this work we did up here. So we can see the y-intercept is equal to delta S over R. So since the y-intercept B is equal to delta S over R, we can say that we can solve for delta S. So delta S, we're going to multiply both sides by R. So we get R times the slope is going to give us our delta S. So delta S is equal to 8.314 joules per mole per Kelvin. And our y-intercept is 22.49. And we have to figure out what the units are for the y-intercept. Well, the y-intercept units are the same as the units for y. And because this is a log function, we know that it's going to be unitless. So our units for y-intercept and for the slope are going to be the same units. And we can see those are entropy units, right? Because we've got a joule per Kelvin for those units. We have 8.314. We have 22.49. And that comes out to 187 joules per mole per Kelvin. Okay, so we can get the complete thermodynamics of the reaction by plotting the equilibrium constant, or log of equilibrium constant, as a function of reciprocal absolute temperature. All right, number 4. Consider the reaction below. We're given a bunch of things: delta G standard, delta G, temperature, and concentration of B at equilibrium. And we want to find an expression for the concentration of A at equilibrium. So we know that the delta G and the delta G standard are related by this equation, delta G standard plus RT log of Q. And Q is products over reactants at equilibrium. So we can plug that in here. So Q is equal to B over A, and we got to square the B because it's got 2 there. And we could also just as well write K is equal to B squared over A at equilibrium. So there's 2 different ways of solving this. And they're both equally valid. One's a little bit shorter than the other. I'll do sort of the long-winded one first and then the short one. The long-winded way is to say that this expression here is true at any place during equilibrium, and that K is a subset of, or Q is a subset, K is a subset of Q. So I could just write this out like this and ignore the fact that I'm at equilibrium. If I do that, it'll take a little longer than the shortcut we'll do at the end, but I'll just show you how you would do this. You would solve, you'd say delta G minus delta G standard. We're going to try to solve for Q is equal to RT log of Q. And then we could divide both sides by RT. And then I could take the exponential of both sides to solve for Q. And I know that Q is equal to the concentration of B squared over A at any time, including equilibrium. So I can always say this. This is always true. And I wanted to solve for A, so I'm going to multiply both sides by A. Oops, that's supposed to be just delta G. Okay, so I can write this, I multiplied both sides by A, I have that. That's equal to B squared. And that's true at any time, including at equilibrium. And then I could just divide by the exponential to say B squared over this exponential, delta G minus delta G naught all over RT. Okay, so I could just plug in all these numbers and I will get A. There's actually a way faster way to do this. So a super shortcut would be to write that delta G standard is equal to negative RT log of K equilibrium, and that K equilibrium is the equilibrium concentration of B squared over A at equilibrium, and we're given delta G standard. So what we could do is just set those equal to each other, divide by negative RT, to get the log of K equilibrium, and then just plug in that that is the log of this expression, right? K equilibrium is this. So we can put in B at equilibrium squared over A at equilibrium. And so the only unknown was the concentration of A. So if we take the exponential of both sides, I'll just move over here, we get E to the delta G over RT is equal to B at equilibrium squared over A at equilibrium. So solving for this, we take the exponential of both sides. Oh, I changed ink on there. So we've got that. We've got to be careful, that's delta G standard, right, that we were talking about. And that's going to be equal to B at equilibrium squared over A at equilibrium. So we'll multiply both sides by A at equilibrium. So we've got A at equilibrium times this exponential negative delta G standard over RT is equal to B squared at equilibrium. So to solve for A, we're just going to divide both sides by the exponential. So A at equilibrium is equal to, so we're dividing both sides by this exponential, so it's going to be equal to B at equilibrium squared all over this exponential. So that's E to the negative delta G standard over RT. Okay, so that's our expression for A at equilibrium. That looks different from our answer up here, but we take that answer up there and plug in at equilibrium, at equilibrium, delta G is equal to 0, right? Because if it were negative, it would go forward. If it was positive, it would go backwards. So if we're at equilibrium, delta Z is equal to 0. And if we plug that in, then we get A at equilibrium. And remember, we're sending this piece I'm circling here to 0 because we're at equilibrium. What do we get? We get that it's equal to B squared. Because we're at equilibrium, though, we have to write equilibrium there, over e to the negative delta G standard over RT. So we get the same answer. It's just that this second method that I showed you is a lot faster, right? Because we went immediately to saying, oh, we're looking at for equilibrium concentration, so we can use K instead of Q. That's the end of the key for quiz 5. Thank you for watching.